Good day and welcome to Math 111H Calculus 1 Honors, The Joys of X. On today's class we'll discuss some differentiation rules. Recall the definition of the derivative of a function is f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h, if the limit exists. Recall also that the derivative of a function enables you to find the slope of the tangent line at any point x comma f of x where the derivative exists. So the derivative enables us to find the slope of the tangent line, which enables us to find the equation of the tangent line. And later on in this course you'll learn about more examples of applications of the derivative of a function. So to find the derivative of a function, one uses this definition. So we can consider the function f of x as a constant, and then plugging in or just recognizing that y equals a constant has a slope of 0, one can realize that the slope at any point f prime of x is equal to 0. If f of x is equal to x, then the derivative is simply 1. And those are quite well known. They're quite easy to find using this formula. Let's do an example that's a little bit more interesting. We'll consider the function f of x is x squared, and then the limit as h goes to 0 of f of x plus h minus f of x over h becomes x plus h squared minus x squared divided by h, limit as h goes to 0. We expand the x plus h squared and find that we can cancel out the x squareds, leaving us with the limit as h goes to 0 of 2hx plus h squared divided by h. We can factor out an h and then cancel the h's, leaving us with the limit as h goes to 0 of 2x plus h over 1, which is 2x. Some differentiation rules we can prove using the definition of the derivative, and these are very simple to prove, just plug in, are that the derivative of a constant times the differentiable function is that same constant times the derivative of the function. So the derivative of cf of x is c times f prime of x. And the derivative of a sum of two differentiable functions, f plus g, is simply f prime plus g prime. We'll learn after learning the product rule that the derivative of x to the n, where n is a whole positive number, is simply n times x to the n minus 1. And using these rules, we can find the derivative of any polynomial. Finally, let's consider exponential functions. Let's consider f of x is a to the x. Well, we plug into the definition of the derivative, giving us the limit as h goes to 0 of a to the x plus h minus a to the x over h. Using some algebra, we can factor out an a to the x, leaving us with the limit as h goes to 0 of a to the h minus 1 times a to the x over h. We pull out the a to the x since there's no h's in that piece, and we end up that with the derivative of a to the x being a to the x times some constant, that constant being the limit as h goes to 0 of a to the h minus 1 over h. It's a messy expression to try to understand, but it is a constant, and what we can do is we can, for a given value of a, we can plug in various values of h going to 0 and seeing what the value of this limit is approximately. If we plug in a equal 2 and plug in various values of h going to 0, we find the limit to be around 0.69. If a is equal to 3, the limit's around 1.10. We can convince ourselves that this limit ought to be increasing as a increases, and therefore we can suppose that there's a number between 2 and 3 where the limit as h goes to 0 of a to the h minus 1 over h will be exactly 1. We define e to be that number such that the limit as h goes to 0 of e to the h minus 1 over h is equal to 1. And then if we were to plug in f of x equal e to the x, we would find that the derivative is e to the x times 1. So the derivative of f of x equal e to the x is e to the x. So that's a function whose derivative is itself. Let's take a moment for some math culture. There were 3 prisoners of war, an engineer, a physicist, and a mathematician, who were sentenced to 100 lashes each. They are told that they can request something to have on their back for cover before their sentence is carried out. First, it's the mathematician's turn, and he's asked what he wants for cover. The mathematician says, "I don't want anything on my back." The sentence is carried out, and he is left all bloody and in tremendous pain. Next, it's the physicist's turn, and he says, "I'd like a blanket on my back. That ought to buffer the blows." The sentence is carried out, and despite the cover, he's left all bloody and in great pain. Finally, it's the engineer's turn. When he's asked what he wants for cover, the engineer responds, "I'd like the mathematician on my back." Thank you for joining us today. Have a great day, and may the power of math be with you.